So the book is the introduction to biotechnology, and the topic I'm going to discuss right now is your polymerase chain reaction. The polymerase chain reaction is a repeatedly amplifying techniques. Amplifying amplification of DNA molecules. So nothing so important so far. So here the double-stranded DNA into single-stranded DNA pieces. This is accomplished through the heat by heating up to 90 degrees Celsius. The hydrogen bond between those base pairs get destroyed. Not destroyed, that separator break, and this breaking of this bond will release single-stranded DNA pieces. It is, and here it's not advised to go above 100 degrees Celsius because the bDNA, which has water in itself, water is necessary part in this bDNA. In case of your aDNA, there is no water is there, so it's accessible, but up to 100 degrees Celsius. But in case of bDNA, the water content play important role. So if you just increase up to more than 100 degrees Celsius, the water will start boiling, and that cause the deformation in its DNA structure like protein. The water molecules, forget about this thing, just simply let me tell you. The normal DNA has major group and minor group. The major group and minor group is because this water content, the water in this DNA. For example, just think about here written, think about the strand being same distance apart. That means there is no major group or minor group. It's just group having equal distance. So when we add water inside it, and the water will goes and start forming hydrogen bond, and then electronegativity cause attraction. So this leads to attraction of two strands to form a minor group. So the water where it's present, it causes this minor group to form. So the subsequent group becomes minor, and those being separated becomes the major group. So this is the thing. So when evenly spaced strands pulling to them closer means they will be further away from another adjacent turn, hence the rise of major and minor groups. Okay. Anneal. So what is the anneal? The step anneal here refers to the binding of that primer, that short oligonucleotide sequence, complementary sequence, to that of your desired gene to be cloned, to be replicated, is your annealing. That means the primer bind with your DNA molecule, target DNA sample. Okay. So here the PCR primer are short DNA sequence that are complementary to the end of your amplicon. Amplicon is the first segment. The first segment that is taken for cycle to replicate. Okay. To copy, to make the copies. So here written, if your goal is to have many copies of only amplicon, should we consider a concern about the presence of other 5 extraneous form of DNA. So let me show you this in picture, you better understand. So here this is a particular this is a very small fragment of DNA having both sides is your blunt end, not sticky. This is a small fragment of desired gene or desired fragment of DNA that we want to amplify by PCR. We have to first melt at 90 degrees Celsius as written. This causes separation of these two complementary strands of DNA to become single-stranded DNA strand. Then the process is your annealing, where the primer get attached. So here the primer are being designed in such a way that it will goes and bind with in that particular oligonucleotide base present in that desired DNA region. So it only amplify those deep blue color region. But in the very first we have this two strand and those two strands will remain continuous throughout the cycle and will replicate once in each cycle. So ultimately, if we replicate up to 30 times, then we will have 60 of this kind of DNA out of 1 billions of copies of our desired DNA segment. So it's not affecting or making error. Okay, so this is the desired primer. It's written here ABC, that means it has only 3. It's mostly 18 to 24 oligonucleotide primer is being designed, always used to use design, not always. So now the extraction begins. So now you can see the primer is in the 5' to 3' direction. Will start replicating and adding this nucleotide up to this region, that means up to 3 region, in here also in opposite region. So this is the first cycle. In the second cycle, what happened? Again melting, annealing, and this cause this 4 different type of structure. So here we can see after this extending, we'll have this 4 type of different structure. Now we are going to have our desired gene to get replicated, because it's just beginning, because we have filtered out this segment, this segment, this segment, and this segment. Up to this is your second stage, second cycle. In the third cycle, we'll have this kind of structure. I'm just saying, I'm just telling. So this 4 segment, what we get here, we have just separated in this 2. Now melting, annealing. So this will be looks like some kind of this structure, and then after extending, it will look like this. So this is this and this one. This 2 is the desired length of our gene that we want to amplify, and that 2 will be amplified in exponentially, amplified exponentially, but the other remaining are not not amplified in that way. So to better understand what we are going to have after cycles, let's say 30 cycle, we will lose this parental what we call exponential DNA segment. This DNA segment is not going to be in our tube. Okay, this remain constant 1, this also remain constant 1. We will get only 2 of this kind of DNA. Then we will gonna have this kind of DNA, 1 minus the number of cycle. If you have 30 cycle of DNA amplified, then we will have total 58 number of this kind of DNA, and we gonna have our desired gene up to 2 to the power n minus 2n times. This 2 to the power n is the total number of copy of DNA that we will get finally, and this minus 2n is equal to, because of this unrequired DNA that we have, this is going to disappear, so we are not including this. We are including this 1 plus 1 is equal to 2, and here n minus 1, n minus 1. So n minus 1 plus 1 is equal to n minus 1 minus plus 1 is equal to n. So n plus n is equal to 2n. So 2 to the power n minus 2n is equal to the total number of desired clone DNA we will have. So let me go through some text that I have marked somewhere, I think. Okay, so here it's you can see here, if our goal is to have many copies of our only amplicon means this segment, yes, this one, it is our amplicon. Okay, if we want, our goal is to amplify many copies of this amplicon, we will concern about the presence of only 5 extraneous found DNA. This extraneous found DNA is this DNA segment. Yes, this is going to disappear, not included. So here 1 2 3 4, these 4 are extraneous DNA, and after completing the cycles we will have only one of this kind of extraneous and one of this extraneous, all total 2 of this kind of extraneous DNA, and a 2n minus 2 number of this kind of extraneous DNA, and 2 to the power n minus 2n number of desired DNA. Okay, so what else written here, let me check this out. This means about 30 cycle PCR we will have 60 molecule of double-stranded DNA that contain our extra nucleotide sequence, but we will have about 1,073,741,764 molecules of double-stranded DNA that is strictly represent the amplicon. That means we have that desired gene to get amplified in that huge number. It is theoretically, but practically that doesn't happen, because sometimes because the affinity of that primer to always 100% bind all those fragmented DNA is not always possible. So it is little bit different. We'll discuss coming with through. So here the color is dark blue, something I have to explain. The dark blue is a desired gene we want to amplify. The side blue light sky color is your extraneous nucleotide, and this is the primer in your red color. Orange color is the fragment we want in a PCR. The light orange, this is unrequired fragment DNS. Okay, so this is the thing. Now we are having the steps. So annealing is a term which given the process whereby the primer attaches to the single-stranded DNA. The temperature is much lowered. 90 degree used to melt the double-stranded DNA. A temperature that high will also prevent the binding of primer to single-stranded DNA. So the GC base pair involves 3 hydrogen bonds, while AT base pair only involves 2. It should be apparent that more energy will be required to separate GC primer. So just forget all those I have read now. G and C pair by triple hydrogen bonding, whereas your AT formed by double hydrogen bonding. So if your primer and your product DNA, I mean the DNA you want to clone have a multiple number of GC complementary base pair, then there will be require of more amount of energy required to break those bonds. If there is made of only 80 kind of base pair primer design, then there will be less energy required to break those bonds. So to maintain those temperature requirement and to stabilize the structure within a critical temperature, because if the GC require high temperature and the AT require low temperature, and we are making of this gradation, it will be difficult for annealing process. So we have to design our primer in such a way that there will be about 40 to 60% of this AT and GC pairing. Mostly we considered 60% of GC and 40% of AT bases in our primer design primer. So this is the thing. So, and also think about that it's written, if we had a hot 95 degree solution of single-stranded DNA plus 2 primer which will be cooled gradually, then the lower temperature will still have your GC bond, because it's required, I mean the GC primer will be bind the target first. That means if we have the primer and your DNA, then with lowering temperature from 95 degrees Celsius to 72 degrees Celsius, the first release will occur from this your GC, then your AT. Similarly, if we enhance the temperature, the AT bond will break first, then your GC bond. That's the thing I want to tell you. Okay, So it's better to have make a design a primer which range will be between 58 to 62 degree Celsius. And it also required that we have to design in such a way that the annealing temperature remain lower than your extending temperature. Getting my point? Because if they're not properly annealed and we are carrying out our extension, then it will be problematic. It won't occurs. So this is the formula, and here it's written here for short sequence up to 20 base pair, 2 into 80 plus 40 GC. The ratio is like your 60 to 40. Formula is there. Also, one thing is that the reason why we chose high annealing temperature to prevent non-specific binding. It is desirable to have an annealing temperature that is relatively high, but it must be cooler than your temperature that will be used for your extension. Just think about in this picture. Okay, so here those primer are anneal with your rigid jet, and now they have to undergo your extension process. So this is extension occurs if this temperature of annealing is if the temperature of your annealing is lower than your extension temperature, then they will separated, and as there will be no primer, so there will be no extension, even though there is a presence of DNA polymerase. DNA polymerase only replicate the DNA when there will be a primer, and due to this high anneal temperature then your extension temperature, there will be no primer attached with that of your desired gene, so there will be no replication. So the annealing temperature must always lower than your extension temperature. Now this is the formula, and this is also written why the desirable to have annealing temperature that is relatively high, but it must be cooler than your temperature for extension. Okay, so extension temperature is always high than your annealing temperature, and but we should not decrease our annealing temperature lower, because it will also decrease your specificity. So we must maintain our temperature in between, not higher than extension nor lower than your specific binding, because if you lower the annealing temperature, the nucleotide will bind to other, their complement, not bound properly with their complementary base pair. Okay, so this means that at the restrictively high temperature of annealing, non-specific binding will be prevented. Extension. Before going to show you extension, you better show this picture. See this picture is important. So in this picture you can clearly see that different steps, different time required for different function. Okay, now let's come to once again back to this extension process. We have done annealing, we have done denaturation, means separation from double stranded to single stranded DNA. Now the extension process, we are using here the Thermus aquaticus bacteria and their enzyme DNA polymerase, because it is his stable DNA polymerase enzyme, also called the Taq DNA polymerase. Okay, which is better efficiency at temperature 73 degrees Celsius. For example, if we have 1000 nucleotide per, and if its speed is your 1 minute 1000 base pair, and we have a amplicon of length 300 base pair, then it will take about 18 seconds to completely replicate a single cycle. Okay, so this is how we determine the time interval for extension. Okay, Hope you understand. You can see this once again. And okay, now we can continue the repeat the cycle for a theoretical maximum up to 20 times. I have told you once in this before that we can continue to repeat this cycle for a theoretical maximum 28 times, but this theoretical maximum is limited by concentration of DNTP, because in a very small region, small concentration of this DNTP, we can only go through 20 times of cycle, but in reality the maximum number of repeated cycle will be higher. And why? The maximum number of repeated cycle will be higher because the efficiency, if all those small DNA will able to bind their primer, then they will all copy replicated exponentially. But it's possible? Practically no. 100% binding to each of these small DNA with primer is not possible. So it's written here, the efficiency to bind this single stranded DNA with primer is less than 100%. It's practically. So we will not have that much replicated copies of our desired gene. So this is the thing. Okay. Now what is PCR loops? You can see here PCR takes place in very small tube up to 200 microliter tube, what we call PCR tube, and in that large volume of 200 microliter we have only 25 microliter of our solution is there. And this is the thing, temperature is there to run those annealing typical following. I have shown this picture you once. So this is the thing. The final Fourier step is simply to hold the sample until the operator returns and collect it. Nothing to understand so deep. So here you can see 28 time we will have used larger number of DNTP to run 71 cycle to PCR to obtain 200 copy of 3 base 1 applicant will be required. That will start over a mole of DNTP. This is unrealistic. Even running 50 cycles will require use over 1 million DNTP in the reaction tube. So this huge amount of this DNTP's cycle in the very small space, and this gradually decreasing amount of your DNTP will start after certain cycle. It will slow your amplification rate, and after some time, because of complete absence of DNTP, there will be no further cycle of your DNTP. So we have to be set our machine in such a way to obtain this much amount of cycle. Okay, this graph will better let you show. This plateau is just is your stage at which your all DLTP are finished, and there will be no further copies of your amplicon, or what we call during early cycle the number of DNA strand will be increased exponentially. However, at the concentration of DNTP decreases, the rate of increase in the number of strand DNA will be also decreases. The DNTP number decreases, the number of double-stranded DNA copies also will decreases, and the rate of double-stranded DNA increases will deaccelerate, eventually coming to a plateau. Means a constant amount of DNA will be present even if further cycle were performed. This is your plateau. This is your plateau region. Okay. Cycle number, how it becomes stable, not increasing anymore. Application of PCR in next video, and that's important also. Okay, thank you very much.